Welcome. Over this course, we build a real, working chatbot called Policy Copilot, from an empty folder to a live deployment on the internet. It answers company policy questions using only the official employee handbook, and it gives you a citation every single time. The way we learn is build first. The moment the build needs a new idea, we stop, name it out loud, and wire it straight into the code. So by the end, you won't just have an app, you'll be able to point at every piece and say what it is and why it's there. Before we write a line of code, let's look at the finished thing. This is the app deployed live right now, answering a real question about company policy. Notice two details. The answer is grounded in the handbook, not made up, and there's a source pill pointing right back to the document it came from. By the end of this course, you'll have built and deployed exactly this, the same app running at a public web address you can share. Here's the map of the whole build. And notice it's also a map of how these systems work. Steps 1 and 2 set up the repo and load the handbook PDF. 3 and 4 cut it into chunks and turn them into embeddings. 5 and 6 store those and search them. 7 and 8 ground the answer and stream it back with citations. And 9 and 10 add the web UI and deploy it to Railway. Every file is one idea in plain code with no framework hiding the mechanics. The whole pattern has a name, Retrieval Augmented Generation, or RAG. It's just 3 moves. First, retrieve. We find the handbook passages that actually relate to the question. Second, augment. We paste those passages into a grounded prompt so the model answers from them and nothing else. Third, generate. We stream back an answer that cites its source. That's the entire idea. And over the course, we'll build each of these 3 moves in turn, one at a time. Let's start where every real project starts, with nothing. In this chapter, we set up 4 things, and that's the entire foundation. A folder to hold the project, a Git repository that we make public on GitHub, a Python virtual environment, so our libraries stay isolated, and the small handful of packages this whole build needs. That list is short on purpose. FastAPI and Unicorn to serve it, the OpenAI SDK for the model, NumPy for math, and pypdf to read the handbook. That's it. Here's the real setup, exactly as you type it. Make a folder and step into it. Run git init to start tracking history. Create a virtual environment with venv and activate it, so these packages install into the project and not your whole machine. Then one pip install line pulls the entire toolchain. FastAPI, Unicorn, the OpenAI SDK, NumPy, and pypdf. Finally, repo create makes it a public repository on GitHub. We keep the dependency list this tiny on purpose, so nothing hides the mechanics we're here to learn. And there it is on GitHub, already public and licensed under Apache 2.0. That means anyone can clone this repo, read every file, and follow along line by line, from this first commit all the way to the live deployment. Building in the open isn't a detail here. It's part of the point. Every concept we name will live in plain, readable code you can inspect for yourself. Before we build anything, one file earns its place, config.py. This is central configuration. It reads settings once from the environment and hands them to the rest of the code, so nothing else ever touches os.environ directly. That's why the same code runs on your laptop and up on Railway. Look at what lives here, the chat and embedding model names, and the RAG knobs. Chunk size, chunk overlap, top K, and the minimum score floor. Those few numbers are most of what tunes a RAG system, and we'll meet each one as we build. Ask a plain language model about your vacation policy, and it will answer with total confidence. 25 days, unlimited, whatever sounds right. The problem is it was never told your policy, so it just makes one up. That behavior has a name, hallucination. For an HR or policy bot, a confident wrong number isn't a quirk, it's a firing offense. What we actually need is an answer grounded in the real Northwind Robotics handbook, with a citation back to the source, and an honest, I don't know, when the handbook simply doesn't cover the question. So how do you give a model your documents? There are really 3 ways. You could paste the whole handbook into every prompt. Simple, but it's costly, it slams into the model's context limit, and the one relevant line gets buried in noise. You could fine-tune, training the model on your docs, but that's expensive, painfully slow to update, and it still hallucinates. Or you retrieve just the handful of passages that matter for each question. That's RAG, and for a document that changes and must be cited, like a handbook, it's cheap, it updates the instant you edit the file, and it's easy to cite. Here's what RAG actually does in 3 moves. First, we retrieve. We embed the question and find the closest handbook chunks. Then we augment. We drop those chunks into a strict, grounded prompt. Then we generate. The model answers only from what it was handed. Here's the key insight. The model never memorizes your handbook. It stays a general model, and we hand it the right pages at question time. That's exactly why editing the handbook updates the answers instantly, with nothing to retrain. That augment step hinges on one thing, the system prompt. This is where we introduce grounding, the rule that forbids the model from using any outside knowledge. Look at these instructions. Answer strictly from the provided context. If it isn't there, say so and suggest people ops. Cite the source in brackets, like handbook.pdf. Never guess a number. That single paragraph is the whole trick. It's what separates a trustworthy policy bot from a plausible liar. Every honest answer this bot gives has to come from somewhere. That somewhere is one file, a fictional employee handbook for a company called Northwind Robotics. It's a PDF full of real, specific rules. 20 vacation days a year, 16 weeks of paid parental leave for birthing parents, expenses submitted through a tool called Ramp. This one document is our single source of truth. Everything the assistant knows and everything it's allowed to say will come straight out of this handbook. Here's the actual handbook. 10 sections, all written in plain language, all packed with concrete numbers a person could look up and act on. Nothing about it is special to our demo. In the real world, you drop in your own company's PDF instead, and nothing else in the build changes. The code doesn't care whose policy it is. It just reads whatever PDF you hand it. Now, the first real step of turning that PDF into something a computer could search. It's called text extraction. The library pypdf opens the file and, page by page, pulls the text layer off each one, and we join it all into a single string. That's the function pdf__text, and it's genuinely this short. But real PDFs are messy, stray line breaks, odd spacing, columns that don't line up. So the very next step takes this raw text, cleans up the white space, and splits it into pieces we can actually work with. Let's run it. First, we generate the handbook PDF, then we run the ingest module once. Watch what it does. It reads the handbook, breaks it into 8 chunks, and turns each chunk into a vector using the embedding model, then saves them all into one file, index.mpz. This whole process is called ingestion, and the key word is once. It happens offline ahead of time. When the server is live and answering questions, it never rereads the PDF. It just loads that finished index, which is exactly why answers come back fast. You can't hand a language model the whole handbook as one giant blob. Retrieval needs small, focused pieces it can match a question against and hand back the exact passage that answers it. So before we embed anything, we cut the handbook into overlapping slices. This is called chunking. Our chunks are about 900 characters each, with 150 characters of overlap shared with a neighbor. Small enough to be specific, big enough to hold a whole rule. Here's chunk_text doing exactly that. First, we normalize the white space, collapsing every run of spaces and new lines into one. Then a window of size characters slides through the text. Before we cut, we back up to the nearest space near the end, so we never slice a word in half. We take that slice, and here's the key move. The next chunk doesn't start where this one ended. It steps back by the overlap, so each new chunk begins a little before the previous one finished. Why does the overlap matter? Picture the sentence spelling out parental leave, 16 weeks for birthing parents, sitting right on a chunk boundary. With no overlap, the first chunk ends mid-sentence, and the second one starts mid-sentence, so neither chunk holds the whole rule. Ask the bot about parental leave and retrieval, can't find a passage that actually contains the answer. Add 150 characters of overlap, and both chunks carry the full sentence. Nothing important falls through the cracks. Let's run it. Point ingest at the handbook, and it splits into a handful of overlapping chunks. Here, 8 of them, each around 900 characters with about 150 shared with its neighbor. A bigger document just means more chunks. The idea doesn't change. And those two numbers, chunk size and overlap, aren't hard-coded magic. They live in config, so you can tune them per document. To retrieve the right handbook passages, we first need a way to compare meaning by machine, and that's what embeddings do. An embedding is a model that turns any piece of text into a list of numbers, called a vector. The trick is that texts with similar meaning end up close together in that number space, and texts about different things land far apart. So instead of matching words letter by letter, we can search by meaning. That single idea is what makes the rest of this chatbot possible. Here's the whole embedding step in one function. We send our chunks to the embedding model in a single call, and it hands back one vector per chunk. We stack those into a number py, float 32 array. Then comes the important move. We normalize each row to unit length. That's a small trick with a big payoff. Once every vector has length 1, measuring similarity later is just a plain dot product. No extra math, no division. Normalize now, and cosine similarity becomes a single multiply and add. So why does searching by meaning actually work? Because both the chunks and the question go through the same embedding model. They live in the same number space. Every chunk becomes a point. When someone asks about time off, that question lands right next to the handbook's vacation section, even if it never uses the same words. Ask about PTO, and it finds the passage that says vacation. Closeness means similar meaning. Keyword search would miss that match completely. Embeddings don't. Let's see it land. Our handbook came out to 8 chunks, and calling the health endpoint confirms the service is up and the index is loaded. Behind that number, each of the 8 chunks is now a vector of about 1,536 numbers from text, embedding 3 small. Embedding a whole handbook like this costs only pennies. And now every chunk is a point we can measure a question against. Vectors that point the same way mean the same thing. The phrase vector database sounds like a heavy piece of infrastructure you have to go by. Let's demystify it. At its core, a vector database is just 2 things: a matrix of embeddings, 1 row per chunk, and a function that finds the rows most similar to a query. That's it. We're going to build the whole thing in about 40 lines of number py, so you can see for yourself there's no magic hiding inside. Here's the heart of it, the search function. One line does the real work. We multiply our whole matrix of vectors by the query vector, and in that single matrix vector multiply, every chunk gets scored against the question at the same time. Then we sort the scores from high to low, take the top few rows, and return their text and sources. That's the entire search, and that score has a name. Because every row is a unit vector, the dot product is exactly the cosine similarity between the chunk and the question. Let's score some real chunks. We ask how many vacation days you get, embed the question, and let search rank every chunk. Look at the numbers. The vacation passage comes back on top at 0.63, well ahead of the rest. Higher cosine means closer meaning, so the top chunk is the one that actually holds the answer. And keep an eye on those scores, because in a moment, they'll let us set a floor and refuse to answer when nothing scores well enough. Now, connect this to the real world. Pinecone, Chroma, Vector, the product people reach for, are this same idea. Where we keep a number py matrix, they keep a managed index. Where we do a dot product top k, they run approximate nearest neighbor search. Where we save one .npz file, they persist it in a hosted service. They add scale, filtering, and durability on top, but the core is what you just built. Once you understand these 40 lines, none of those products are mysterious anymore. Retrieval is the RN-RAG. We embed the incoming question with the same model as the chunks, then find the top few chunks that sit closest to it in meaning space. But there's a second, crucial job here. If nothing is actually close enough, the bot must refuse instead of answering from junk. So we enforce a minimum similarity floor, a line the best match has to clear. Clear it, and we ground the answer on real passages. Miss it, and the honest reply is, I don't know. Let's walk it. First, we embed the question. Then we pull the top 4 closest chunks by cosine similarity. Then the important line. We throw away any chunk whose score falls below the floor. If that filter leaves nothing, we hand the model no context at all, and the grounded prompt from the last chapter makes it say it doesn't know. This is a guardrail, so name it. It's a minimum similarity floor, set here to 0.22. And notice get_store. The __ cache means the index loads once and stays in memory for the whole process. Now watch the floor do its work. Ask something the handbook actually answers. How many vacation days do I get? And the top chunk scores well above the floor. So we keep 4 solid passages. Now ask something off topic. Can I bring my dog to the office? The handbook says nothing about dogs, so every score comes back weak and clustered together, none of them clearing 0.22 by any margin. The filter drops them all, and the bot honestly says the handbook doesn't cover it. So the whole retrieval path lands on one of 2 outcomes. We embed the question with the same model as the chunks, take the 4 closest by cosine, then apply the floor, which may drop weak matches all the way to 0. Find something, and those passages ground the answer. Find nothing, and that feeds an honest refusal. Both are correct behavior. This is the A in RAG augmentation. We take the passages that Retrieval handed us and paste them straight into the prompt as context, wrapped in strict rules. Answer only from these passages. Cite the source file. And if the answer isn't in here, say so instead of guessing. This is the step that turns a general chat model into a policy bot you can actually trust. The model isn't recalling anything from training. It's reading the handbook we put right in front of it. Let's walk it. The system message sets the rules. Answer only from context, cite the handbook file, never guess a number, and if the answer isn't there, refuse and point to people ops. Then build_ messages assembles the conversation. It starts with that system message, optionally adds the last few turns of history, and appends 1 user message. That user message literally contains the handbook excerpts, followed by the question. So the model answers from text sitting right in front of it, not from memory. Here's what the model actually receives. First, the rules. Answer only from context, cite the handbook, never guess. Then the context block, holding the real handbook passage word for word. And finally the question. Because the exact number 20 vacation days is sitting right there in the context, the model reports it instead of inventing one. Take the passage away and there's nothing to cite, so it refuses. History rides along too, so follow-up questions still make sense. Let's summarize the grounding contract as 4 rules. Answer only from context, no outside guesses. Cite the handbook file. Every claim stays traceable. Refuse when the answer is absent. An honest, I don't know. And never guess a number. No invented policy. All 4 live in 1 system string. Change that string, and you change the bot's whole personality and safety posture. That single block of text is the difference between a confident guesser and an assistant you could trust. This is the G in RAG generation. We could wait for the model to finish the whole answer and then dump it on the screen all at once. But a chat feels dead if you stare at a blank box for 5 seconds. So instead we stream. We send each token the moment the model produces it, and the answer appears the way a person types. The transport that carries that live feed is called server-sent events. Let's walk it. When we pass stream equals true, the OpenAI call doesn't return 1 finished string. It returns an iterator of deltas, tiny pieces of the reply as they arrive. We loop over that stream, pull the text out of each delta, and yield it onward. That word yield makes this a generator. It hands each token to whoever's listening and pauses, so nothing ever waits for the full answer to be done. Here the 3 RAG steps finally come together inside 1 endpoint. First we retrieve the handbook passages for the question. Then we send the sources down the wire first before any answer, so the interface can paint the citation pills right away. Only then do we build the grounded prompt and stream the answer back token by token and finish with a done signal. Retrieve, augment, generate, all in a single streaming response. Let's hit the endpoint with curl and watch the raw stream come back. The source's event lands first, That's what draws the citation pills. Then a flurry of token events, each carrying one little slice of text, arriving one after another as the model writes. This is the exact same stream the browser reads to paint the answer live on screen. Now we build the face of the product, a clean, Claude-style chat interface, written with plain HTML, CSS, and JavaScript. No framework at all. The whole point is that the mechanics stay visible. It shows the answer streaming in, word by word, and above each answer it shows PIL for the sources the bot retrieved from handbook. So the trust isn't a claim, it's on the screen. This is our web UI. Here's the welcome screen. A warm paper background, a single input box, and a few suggested questions to get people moving. There's no dashboard, no clutter, no settings to learn. The design deliberately gets out of the way. So, a first-time visitor just asks their question and reads the answer. Let's walk the front-end side of streaming. We post a question to /API/chat. Then instead of waiting for the whole answer, we read the response body as a stream. We decode each chunk of bytes into text and split it on the blank line delimiter that separates server-sent events. For every token event, we append its text to the answer and repaint the bubble. That growing, self-typing effect you see is literally just this loop running. And when a source's event arrives, we render the pills. And here's the payoff on screen. Every answer carries source pills at the top, each showing the file it came from and how strongly that chunk matched the question. Down in the text, the handbook citation is highlighted inline. So a user doesn't have to trust the bot blindly. They can see exactly where the answer came from. Here's a design choice that keeps deployment simple. One FastAPI app serves both sides of the product. The JSON streaming API that answers questions and the static web UI that people click on. There's no separate front-end server to run, no cross-origin headaches to configure, and only one thing to ship. The page and the API live at the same address, so the browser talks to itself. One app, one deploy. Let's walk the app. We create one FastAPI instance and hang three things off it. First, a health endpoint that returns OK, the chunk count, and the model name. It doubles as Railway's liveness check, so the platform can tell the app is alive. Second, the streaming chat endpoint we built earlier, the one that pushes sources and answer tokens over SSE. And third, static file hosting for the web UI. The trick is that we mount the static files last, so the API routes always win. One file, one service. Now run it locally with Unicorn, pointing at app.main:app. It boots the whole product in one process. Hit the health endpoint, and you get back OK, the company name, 8 chunks, and the model. That chunk count confirms the index loaded fine. Open the port in a browser, and the chat UI is served by the very same process that answers the questions. No second server. And this exact app runs unchanged in the cloud on Railway. Now it's time to put this on the internet. We deploy to Railway, a platform that builds straight from our repo. There's nothing exotic here. We point at the code, we set one secret, the OpenAI key, as an environment variable, and Railway hands us a public URL. And because our index is pre-built and committed into the repo, the deployed app answers immediately. It doesn't have to re-embed the handbook on boot. It reads the index that's already there and starts serving. Let's walk the Rail commands. First, we init the project, giving it a name. Then we add the service and set the OpenAI key as a variable, right there in the command. Next, we push the code with Railway up, and Railway detects Python and installs from requirements.txt. Finally, we ask for a domain, and we get a public address anyone can hit. Notice where the key lives. It sits in Railway's variables, never committed to Git. That separation is the whole point of an environment variable. 2 tiny config files are all it takes to make this deployable. The first tells Railway how to start us. Bind to all interfaces on the port Railway injects at runtime, not a hard-coded local host. The second piece is the health check. We point it at our /API/health route, so Railway can ping the app and know exactly when it's up and ready to take traffic. And here's the nice part. The repo is public and the service is live. There's no secret sauce locked away. Anyone can clone it, point Railway at their own copy, set their own OpenAI key, and have their own policy bot running in minutes. Everything you watched us build is right there for you to take and make your own. A deployed bot isn't done until you try to break it. So we test a live URL two ways. First, a question the handbook actually answers. It must give the real number and cite its source. Second, a question the handbook never covers. It must refuse instead of guessing. That pair is how you know the grounding and the score floor are really working, not just on your laptop, but in production where real people will use it. Here it is on the live site. We ask a real policy question, and it answers with the exact figure straight from the handbook, then marks where that figure came from. Nothing is invented. Nothing is rounded from memory. The number you see is the number in the document. With a citation, you can check. Now run both cases against production with curl. The vacation question comes back with the real number, 20 days, and a handbook citation in brackets. Then the dog question, which the handbook never addresses, gets an honest refusal that points you to people ops instead of making something up. Cite when it knows, refuse when it doesn't. That's the whole safety story working end to end on a live URL. Let's tie it together. Every trustworthy behavior maps to a concrete mechanism you built. It answers from the handbook because of retrieval and a grounded prompt. Every claim is cited because the system rule demands it. It refuses the unknown because of the minimum score floor at 0.22. And it never invents a number because we told it never to guess and gave it only real passages. Trust here isn't a feeling. It's engineered line by line. Step back and look at what's on screen. A real RAG chatbot built from an empty folder running live on Railway. Let's name each concept you can now point to. Ingestion, pulling the text out of the handbook. Chunking into 900-character passages. Embeddings, turning those passages into vectors. The vector store, holding them in NumPy. Retrieval, the cosine top 4 search. The score floor at 0.22, so it can say I don't know. Grounding and citations, forcing every answer back to the handbook. Streaming over SSE and a one-service deploy, because you built each piece the moment you needed it. These aren't abstract terms anymore. They're things you wired in with your own hands. Here's the map, and it's simple. Each file is one idea. If you ever forget what retrieval means, open retrieve.py, and it's right there in a few readable lines. Ingest.py is chunking and building the index. LLM.py is embeddings and streaming. Store.py is the vector store. Prompts.py is grounding and citations. And main.py ties it all into one streamed FastAPI service. Open any file, and the concept is right there in plain code. The project is public and Apache licensed. Clone it, swap in your own company's handbook, set your key, and deploy your own policy bot. If building it first and naming each concept as you hit it made this click, subscribe, and tell me in the comments what document you'd point it at. The repo link is in the description. Now go make it yours.